Good afternoon, everyone. I think we'll get started. It's 12:40 on my computer. So we are now starting the In Situ session. We have two speakers, and this session is sponsored by S2 Environmental. Thank you very much, S2. Shall we roll video for S2, please? Great, thanks for that. So hi everybody, my name's Holly Kingston and I work for the Canada Energy Regulator, and I'm happy to moderate this In Situ session this afternoon. Thanks everyone who's attending, and thanks to our speakers. We have Bud Ivy and Jean Paré. So we're going to start first with Bud's presentation. I'm just trying to find the title here. Here we are. So the title is Surfactant Enhanced Extraction at El Napo and DNAPL Impacted Sites, Pilot to Full-Scale Applications in Canada, United States, and Europe. Sounds great. Take it away, Bud.
Okay, getting my timer. There we go. You can see my screen okay?
Yep,
okay.
We see it.
Okay, just wanted to make sure because sometimes it doesn't happen. Anyways, thank you everybody for participating online to be at the RemTech. This is great. I'm giving you a presentation, as you said, surfactant enhanced extraction at El Napo and DNAPL sites. This can have somewhat certain technical aspects of the site to kind of maybe change the way you look at El Napo and DNAPL behavior. We tend to think, oh, it's El Napo that floats, DNAPL it sinks. There's a little more going on to it. I'm actually a synthetic organic chemist that also did geotechnical engineering, so I have a very multidisciplinary view on things. So I'll try to share some of that with you so that you're able to understand my view on things. With that said, I'm getting my slides going here. If you'd like a copy of my presentation, I think Joe's going to put it up, or if somebody would like a copy, otherwise feel free to email me. My information will be at the back, so feel free with that. I was also moderating the regulatory and legal update session yesterday, and I think from a due diligence perspective, I like to bring this slide up a lot when I'm talking United States. The products that we developed at Ivy are free of unwanted impurities, no PFO, no PFOS, no 1,4-dioxins, no dioxins, furans, no PCBs, and we've been tested free of every US EPA regulated compound, and we continuously work to evaluate new emerging contaminants to make sure we're free of those. So we're helping you with your due diligence so you're not introducing something at your site that you don't want there. Now, when we deal with El Napo and DNAPL, as I said, I want you to think about things differently. We tend to think of El Naples because they don't dissolve, they float. DNAPLs, since they are a bit more dense, they tend to sink. But they're also things that form globules, and they also have a tendency of absorbing onto soils. And that creates a bit of a challenge for you in how you want to deal with them. And they tend to be somewhat challenging to get through things. They also tend to block up effective pore spaces and pathways when you're trying to deliver things or trying to extract them, which makes it a bit difficult to deal with. So we often look at solubility and density as ways to evaluate this, but there's a bit of an error in doing so. The best way to really look at when you're dealing with trapped gases or trapped liquids like petroleum or chlorinated solvents is interfacial tension. And that really comes into play as to how well these things can move through a porous space. And if anyone's ever dealing with unconventional gas, like gas recovery from fractured bedrocks and things like this, a lot of that gas is actually trapped by water. And until they can open up that pathway, it doesn't get out. So getting that out is very, very important. So we'll get into some of that today. So we know when we have a source of spill, if it's LNAP, we tend to think it's going to float on the water and use that as a pathway. If it's heavier, it tends to move along a bit further. However, when you're on site, it's not quite that simple as sinking or floating. This is actually a bailer from a site where we have LNAPL and DNAPL contamination, and we have some phases that are in between. So it's not quite simply that something's going to float or sink. There's a lot more going on in that play. So here's a couple images I've done where I'm talking about soils, vapor, water, and contamination on sites, and we're trying to get that out because obviously we're trying to remove them physically, chemically, or biologically. That's the only three options. But we have to understand when you're trying to move that gas to multi-phase extraction, or you're trying to draw that groundwater that's just trapped, maybe it's plugged because there's some kind of oil or chlorinated solvent in the way. Interfacial tension really drives a lot of what's going on. Some people think it's limited to hydrostatic pressure. There's a huge error in that. If you're a person that does paddy dive and you're going down 15, 30, 60 feet, hydrostatic pressure is important there. It's not always as effective to say at 15 or 20 feet below the ground surface that that's at play equally from the ground surface down. So there's a lot of other things taking place in there. So interfacial tension really tends to play a big thing. Other things, when you have these things stuck in there, they actually close off pathways and cause pathway interference. So sometimes clients use me to remove some of these contaminants and open up pathways before they do a secondary physical, chemical, or biological action on sites. Just showing LNAPLs, just showing vapors that are stuck in sites, so you want to get these out. Getting back to my point about interfacial tension, showing some floating and sinking products. Well, water has a surface tension of 73 dynes, while groundwater has contaminants tend to have about 21 to 23 dynes. So you can see that, from just a sheer force perspective, those contaminants can't really move by that water, and it kind of blocks its movement. So it gets stuck there. So as I said before, when you're looking at LNAPLs and DNAPLs, it's not quite simply think of floatings and sinkers. Here's a really interesting photograph. And what I'm trying to show here is there's a ping pong ball, which is not very dense, floating on lamp oil, which is on top of rubbing alcohol. There's a soda cap floating in there. There's vegetable oil. There's a bead. Then there's water, a cherry tomato, which has kind of an intermediate density, dish soap, a dye, milk, a maple syrup, popcorn kernel that's a bit dense, but not as dense as most things, corn syrup, honey, and there's actually a brass bolt at the bottom. And if anyone's ever gone to a bar, we have a really good mixologist. They sometimes actually play and create layers in your drink, showing there's a lot of different densities. And there's a lot of things that you guys would typically call organic compounds here or oil range compounds here. And you can see they have different densities. So different things come into play, which affects their behavior. Now, when you're dealing with contamination that doesn't dissolve, it tends to absorb onto surfaces. And what I'm showing here on the left-hand side is sorbed contaminants on surfaces. You can also think of globules or a layer of free product floating or sinking. They tend to do the same thing, and they don't get into that water quite so easily. There are, again, density factors, solubility factors, but they tend to phase partition. That even happens when you have things such as PFAS, and there's a lot of organic content in the soils. And since we've had a lot of forests and things like that in history, there's usually organic content in soils. So what you want to do is take them from where they're at here on the left side where they're less available, and you want to make them more available. So again, whether blocking pathways or you just want to make them more physically, chemically, or biologically available, it's possible. And those are some of the things that we work on in trying to change the behavior of the way some chemicals work and whatnot. Now, when we're dealing with things such as bioremediation, we know that some people, when we're dealing with spills or remote sites, we sometimes look at biological remediation techniques. And that just speaks to the physical, chemical, and biological limitations of these sorbed contaminants or globules or free phase. So this quote's a good one because it's from 1995. And this quote speaks about issues going back to the 1990s. And it says, during the past decade, much discussions have centered on the unavailability of sorbed compounds to soil microorganisms. It's now generally assumed that desorption and diffusion of bound contaminants to the aqueous phase is required for microbial degradation. But it doesn't stop there. We know that's also true of MPE, pump and treatment, or even chemical processes, oxidation reduction, amongst other techniques that you can use to actually degrade these things. If they're less available, those reaction kinetics or those physical interaction kinetics are greatly reduced, okay? So getting back onto that, if you do have absorption or globule or free phase formation, you're limiting their mobility and you're limiting their availability. And in terms of physical availability, multi-phase extraction, I've seen a lot of sites where they're doing it, getting lots of mass out, they're really happy, and all of a sudden it tapers off. And they're like, oh, maybe we should pull the system. I'm like, whoa, whoa, it's got all the readily available stuff. It's that absorbed phase, globules, and free phases having a hard time with. You may be able to enhance that process. Biologically, if you're ever doing any F3 or F4 bioremediation in Alberta or Western Canada or upstream situations, those tend to absorb and they're less bioavailable. There's lots of energy in them for bacteria. So if you can desorb them, the bacteria will act on them quickly. Also chemical availability, chemical oxidation, reductions, combinations thereof, as well as the 4 other class of reactions we're not currently doing that I think would come into the remediation field quite nicely. You can improve those as well. I also find some people will go in and remove free phase because stoichiometrically it's too expensive to treat by chemical oxidation reduction. So remove that, and then when you got that down to a sheen or lower levels, then follow up with your physical, chemical, or biological methods to resolve it. And that pairing's working well. So don't be afraid of combining technology. So how does IvySol work? I realized that when you're looking at chemicals, they all have different chemical features. So joke looking at a human, we have an ear, a nose, an arm, a hand, a foot. Well, I developed a way to actually have affinity for those regions of molecules that can develop formulations, can pull them in solution. And what you're seeing here could be like Zorb phase or L-NAPL or D-NAPL, pulling it into solution at the molecular level and making it miscible without encapsulating it. Because if you encapsulate it, you reduce its availability. You don't want that. You want to preserve that availability. So that's what we're doing, working below the critical micelle concentration. This image I just put up in the upper right is actually what 99% of most surfactants work. They completely encapsulate it. Well, if you're completely encapsulated, good luck at physically getting at that chemically or biologically. It's really hindered. Now try to take that basically emulsified oil droplets and run them through an oil water separator. It won't work. Activated carbon doesn't work, so you don't want to do that. So that was a key in the process that I was looking at as an organic chemist. Could I come up with a way to work below the CMC? And we've done that, and we've patented it. Because of that, we have different formulations that you can use on different types of contaminants. So if you use 106 on gasoline, it's not going to work as well as you'd like it to. Same thing if you're dealing with motor oils and lubricants, you got to pair up the application very well. We also have people that are looking for 1,4-dioxane-free decontamination products for cleaning field equipment, storage tanks and whatnot, and that's where Deconic came from. Moving on. Oh yeah, the other thing too is because we are working at very low concentrations, please dilute our products about 1 to 50 with water for most applications. The highest I see is maybe 1 to 25. I have some people using clean room decons for aviation fields that work with us. They're using 1 to 100 to decontaminate surfaces. Now, not only have I talked about you look at the way you look at contaminants differently, I'm gonna actually look at water differently. You've all been taught water is H2O. Well, it's not quite the truth. Here's a bead of water on fine sand. Shouldn't that be going in? So what I tend to say when you see something like this, what's going on is the first thing that comes to your mind. Well, in this vision you're seeing right now, what you see at the macroscopic level speaks to what's happening at the microscopic or at the atomic level. So I'm going to kind of explain to what water really is, because it's not really H2O. That's just a representation of what it is. So we tend to know that things in the upper right-hand side of the periodic table are like oxygen, sulfur, chlorine, or should we say electronegative? So we use delta negative by the oxygen. Hydrogen, like where sodium and say calcium are, they're electropositive, so we use that again delta positive. And in doing so, we can basically start to describe the behavior of a lot of molecules like very much like magnets. And we were taught in like junior high or high school, and maybe in introductory chemistry in university, about how one oxygen molecule and one molecule will be attracted to the neighboring hydrogen, doing something called hydrogen bonding, which gives rise to why you get, when you do a belly flop, it hurts. Well, that's not the entire explanation. What you need to understand is that not only does it reach into a molecule here, it's doing it in every direction, and that's actually forming something that's referred to as a water cluster. So what you are pushing and pulling in the subsurface when you're dealing with lots of silts and clays with smaller pore throats and openings are these water clusters, which are more challenging to move, and hence the K value changes. But wouldn't it be great if we could change the size of that water cluster so it's smaller? Well, with IvySol, not only we can break down things like L-NAPL and D-NAPL and deal with the absorb phase, we can actually also change the size of these water clusters so they're smaller to allow access and regress and temporarily break some rules of chemistry, allowing you to improve K for delivery or extraction. This is a nice way of showing, like, look at these water clusters trying to get into areas that are trapped. And that's where I was talking about some of this impedance that can happen from trapped oils and globules. They actually are closing off some spaces. Well, if you can make those water clusters smaller, you actually have better access to get into those areas to start working on them with the products we have to desorb them, make them more available. So often we're paired with MPE, biological or chemical processes to enhance those. Or put another way, large clusters being smaller and smaller, and the good old fireman has his ability to get in there and put out that fire, but essentially get in there and start working on those contaminants to get them out. So access and regress, or access to those contaminants and improving their availability, is critical. And overcoming things such as interfacial tension are critical for you to have that work, and also do that below the critical micelle so your water treatment system still works. Okay, moving on. Here's another way of looking at interfacial tension. It comes together. You got 73 dynes on one side, maybe 21, 22 in the other with the contaminant. And consequently, those phases aren't coming together. That's why you see oil floating on water or chlorinated solvent sinking. But if you could find a way to overcome that interfacial tension, as we've been discussing with IvySol, all of a sudden you can make things cross that phase. And when you do so, it breaks down that phase and allows transport or movement. And when you have that taking place, it allows you guys to work on it better physically, chemically, and biologically. So interfacial tension is really, really critical here. Nice little images of some stuff that we've done in that very vein of working with clients with L-NAPL and D-NAPL contamination. I'm going to show a couple quick animations here, and I'll explain them as we go. Oh, hang on. There we go. So you go into a site, you investigate it, as we all do, right? And we determine vapor, soil, groundwater contaminants, the type of contaminants, concentration, and where we sit regulatorily. Is the site clean? Do we want to work on it in situ, ex situ, or do we want to risk close it or what have you? Based upon that information we get from the client, we can then do a model with vertical, angled, or horizontal wells so we can inject our products, mostly introduced by gravity. We can put a packer in there. So we inject it. And most of the times, this is called a push-pull, where we inject our products, typically waiting 24 hours. And so it has contact, desorbing all those contaminants, making that L-NAPL miscible, and then we pull it out. So we refer to this as a push-pull. This is very much like a sequential extraction with a solvent that the lab does with you guys with all your samples. Another analogy we get involved with here, I'm going to show, is what we refer to as a sweep. It's probably the second most common strategy we do. That's where clients have contamination, maybe in the central region. We put some injection wells on one side. Maybe there's a pipeline there, fiber optics, or roadway. And the other side, we have extraction wells. So what we do is, under hydraulic influence of the extraction wells, we introduce the IvySol into that subsurface smear zone. Because remember, the water table moves up and down. You'll have that even with D-NAPLs. So we inject our products. It's being hydraulically pulled through that zone of contamination, where it starts to work on the L-NAPL, absorb phase, and globules, making them miscible, whereby you can extract them at the extraction wells at the other side. This animation is quite helpful if you get an appreciation for how that works. And you can take time-based samples to evaluate this and its efficacy for you reaching your cleanup goals at that site. Now, as I like to do, I'd like to show a couple little stories here, a couple case studies that we're involved with. This is a super fun site in New York City that we're involved with. It's with Amtrak. And they had a site that I'll describe here for you. It's a Sunnyside Yard. It had been in operation for over 100 years. You can imagine over that time period, lots of spills. And we really didn't have the regulatory standards back in the day when my grandfather was probably working that we do today. Consequently, there was a lot of, say, accidental releases of materials. They actually have 6 operational units, means 6 areas of highly contaminated spots in the site. It's kind of where my cursor's at right now, that we were doing a pilot scale application where they had a multi-phase extraction system. The main goal here was to get rid of that free phase, which was presenting the greatest amount of risk for the client. So this just details some of the issues they had. With both case studies, we went through a bench scale study to show that our products had the accuracy they wanted and weren't creating any unnecessary issues. In this case, they actually had PCBs in the soil, which had a reasonable cleanup goal for this kind of industrial land use. However, if those PCBs got transferred into the aqueous phase, we all know that the PCB allowable limits in groundwater are very, very low. So that was a concern by the bench scale. We could show that we could make the heavy oil contamination at this site miscible in groundwater with 4 to 5 orders of magnitude over PCB liberation. So we weren't going to cause that issue, which was critical for this client, which also proved out at pilot and full scale. This shows a multi-phase extraction system that they had set up at the site. I'll show you a nice overview of it. There's the treatment system. You can see some of the overland connection to some of those wells. Some actually go under rail lines to wells that you can't quite see on this image, but they had a network of wells they were trying to remove that free phase with. They had some good efficacy early on, which I'll share in this image. This shows the operations between 2013 and 2015. And what's really nice is with multi-phase extraction, it does a great job of getting vapors, dissolved, and free phase out. But at a certain point, right about here, it starts to taper off or becomes we refer to as asymptotic. Your rate of recovery reduces greatly. So at around 5 months, 84% of all the mass they ever got was achieved. And then it became, the system was not getting as much out. So they're really eager to see if they could attenuate that or enhance that. And hence they contacted us again for bench scale. This is the pilot, and it went to full scale, which I'll talk about as well. So I explained to you how the IVSOL worked. I think this image here speaks to what we were doing on this, is again, freeing up that trapped oils, which were actually limiting the ability, even for the multi-phase extraction, to get vapor, dissolved, and free phase. And in doing so, it was a really interesting application for us. They found 8 wells that they found quite troublesome for them. And of course, those are the ones they gave to us to work on. And I've just kind of identified those in red circles here. There they are doing the gravity feed. It's about a 1 to 50 dilution. They want to try some higher, but they realize that it doesn't improve things because of our selectivity. You do not need to work where you make things emulsified. What you're seeing on the bottom right side of the image here is our field test kits, where we can actually inject at a well and see when a surfactant injected at one well extracted to another. In that sweep, in that second animation, you can see it arriving and what the concentration is carrying those contaminants. So this is really helpful, and a lot of clients in the United States like this because it's a real-time field test kit, and we've actually achieved a 96.7% correlation from what we see in the field to what you can actually get at the lab. That was actually validated by a consulting firm in Baltimore, EBA. This is a nice set of results that we went, and actually it was the autumn of 2015 we did this work, and this is the thickness of free phase that was observed at the wells before we did our 1-week pilot involving 3 applications. Of course, like all these things, once you do your pilot, you then go to the regulator, apply for full scale, and these things are not quick in New York. It's a very, very busy state with a lot of regulatory activity. So we didn't actually get around to getting ready to do the next phase of full scale until later in 2016. What's important, here's the pre and post thickness. So the key thing you want to take away from this is that there was no rebound in the contamination levels. What I like to show this is another way. Here's the percent mass removal in 1 week at these wells. And remember, it took them over 2 years, they weren't getting very much out. But the key takeaway here is 81% mass removal on average from all those wells. So that was quite something to achieve. But realize, even though I could desorb or make those globules or free phase miscible, I had to be paired with that multi-phase extraction system, which had really good communication hydrogeologically with the site to pull it out. The key conclusions were the NAPL recovery was increased significantly for them. They're really happy with that. They also noticed that the NAPL thickness they could observe the changes rapidly, literally by the next day. And they also found that although we tend to think more is better, they found, yeah, you're right, Bud, 1 to 50 was better than 1 to 20. And that it worked very, very well in the conditions that we had at the site, which included some very low permeable soils. That pilot led to full scale. I can share that at full scale, it achieved its objectives within 6 months. Just a good time check for me. I got a little less than 10 minutes left. I'll share one more case study for you. This is a really interesting site application we're involved with near Melbourne, Australia. It's a former gasworks type site. So I'll get into that, and actually Daniel Hirth with Biosphere actually led this project and presented at another conference and was kind enough to share these slides with me, which I'm sharing with this community for the first time. So it's a rural gasworks site that was in operation for almost 100 years, and you can imagine the typical contaminants that come with that. So we had a lot of soil and groundwater contaminants and a lot of free phase concerns. What's interesting about this is there's 2 source zones of former tar, liquor, disposal wells, which are shown on the plan. But the key thing is wherever you tend to see here these plumes on the site, where they tend to have naphthalene concentrations that be co-located with a lot of L-naphthalene and otherwise phase contaminants, which I'll talk about in a moment. So that was our objective, to see if we could attenuate that, because they'd tried a lot of things, pump and treat, multi-phase, biological, a lot of things that just weren't achieving the objective. So we went through bench scale to show we had a really interesting efficacy for breaking that stuff up to make it more available. So we're going to try to pair it with their existing system to see if we could, finally get this over the hump and make it work better. Again, the objective was to remove that L-NAPL presence. Obviously, from a risk perspective and regulatory concern, they want to deal with that. They also did things with naphthalene and a few other contaminants of concern, some of which we can also help enhance the removal of. Again, they also want to remove and reduce contaminant liability. And as you probably saw in the former photograph, air photo, there's a residential community in the area. A lot of these former industrial areas, because of expansion of residential areas, kind of move into them and they become co-located, and there's concerns with impacts resulting from them. So obviously we wanted to reduce that source zone contamination as reasonably practical at the site. They had a conceptual model that was quite extensive for the site, because they had well over 100 wells at it, did a lot of really good computer modeling. And the system that they have set up in Australia is quite interesting in that not only do you have the environmental consultant and regulator play, there's also an auditor that's assigned by the regulator to also be involved, so that there's a lot of eyes on everything that you're doing. We talked before about how the IVSOL works. The key takeaway here is we work below the CMC, we can target the contaminants, and that was well known by the client. But the key thing we did was really fun is, as we were applying it, we were seeing how the patient was responding. We used that kind of terminology. Let's try something and see how the site responds. Let's try it. And we were tweaking. We were on the phone every single week, sometimes multiple times, as we were tweaking this over the application period. It was a lot of fun to work with them. This just shows you some of the site workings in the area that we were at and some of the work that they were doing. And so we were doing surfactant-enhanced recovery, coupled with their multi-phase extraction system. So if you ever have a multi-phase extraction system that's kind of, shall we say, not performing at quite the level you want, trust me, it's not time to throw it out. It may be time to enhance it, because they're great systems to work with, and we have a lot of case studies on that. Here's that photo I showed earlier. This first baler actually is comprised of L-NAPL, intermediate, and D-NAPL contaminants. Yes, intermediates as well. And over that course of that period, we actually had to change the formulation of the IVSOL to address all those, which we did. And then, as you can see, as we got going on, then we were targeting thinner and thinner amounts of product over that time period for recovery, and they could really see the results. And we also played with like contact time. So when we introduced the IVSOL, how much residence time should we have? Should it be 24, 48, or it should be 4 to 6 hours? And we started playing with that a lot to really enhance that mass recovery that we realized at the areas. And obviously in areas that they cleaned up, then they would focus their energy on residual areas where impacts were having, and they were still getting significant mass removal. And this graph shows the occurrence over a 180-day period. And just nice little images showing some of the stuff that the client was sharing with me that they're observing over time. There's more photos, but these three really say a lot. So great to work with them. In summary on this slide, the SEER, surfactant-enhanced remediation using IVSOL with groundwater extraction, can be a viable remediation method for tar, L-NAPL, and aquifers that have limited human environmental receptors, unconsolidated sediments, sounds familiar, sufficient effective permeability for L-NAPL entry. And so remember, when spills happen, they've got to move. So whether they get into, as long as that can happen, and then you have to have sufficient interconnected permeability for L-NAPL extraction. So again, what we found is that when the IVSOL was changing interfacial tension, changing the size of water clusters, we allowed access and regress to take place. But again, pairing that with multi-phase is critical, because my IVSOL doing that's not enough. You have to pair it with something physical, chemical, or biological. In this case, it was physical. Sustainable, economic, it was much less cost than other options like co-solvents, thermal, stabilization. Social, they really liked it because there was a lot of interaction with the local community. They really engaged that down there. And there's low noise, low odor, reduced street traffic is what we did. Environmentally, IVSOL is biodegradable. Surfactant reduces wastewater generation. We didn't affect their treatment system. They were very happy that we didn't have any trace residual contaminants. And if anyone's concerned with PFOA and PFOS, Australia, I would say in many ways, if you're looking at what's coming, watch the trends and what they're doing. And if you have long chain PFOS molecules, they're looking at something with a short chain, warning, 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 don't do that. As a chemist, I'm telling you, they're just as toxic. In some cases, I think they're going to be worse. So you're noticing Europe and actually Australia is already making moves to actually ban the short chain versions thereof. So that was good. The real cool part about this too is in January of this year, They actually closed the system off, and it's going through the closure process as we speak. And there's been no rebound of any issues, and it's looking like it's going to go through as it should. So it was a really fun application. But the key part here is having good partners to work with, have really understood the patient from the work that they did. And as we applied it, we evaluated, we did, and we tweaked things as we had to realize a very good outcome in 180 days. They expected it to take a lot longer. So when clients are approaching us about contaminated sites that they have, our process is rather simple. I give a one-page writable site evaluation form, and the things that are in there, honestly, if you grab a cup of coffee, it'll still be warm when you fill this out in most cases. There's a little list of additional things you can share with us about your site so we understand it. Then based upon that, we can do up an in situ model, or if you're doing like surfactant-enhanced bioremediation, this is actually an application with Aloo buckets, or someone's doing soil washing, we come up with those designs as far as product, concentration, and of course, with every application we do, we learn and we carry that knowledge forward. And again, like I was talking before about the selectivity, you have to pair the technology you're dealing with the right product. So we do that. And then dosage, if you have a lot of free phase, we might say do a 1:25 dilution, but we typically would say more than 80% of our applications are done at, if you have LNAP, we might say 4%, sorry. In most cases, it's at a 2% or a 1:50 dilution. As I said, I even have clients doing 1:100s, that'd be more like biological. And then when we do our things, we hang around to support what we sell. And unless it's a really litigious project where you want us very involved, often that's provided without any cost at all to our clients. I also want to share we won a top 10 environmental technology solution providers award back in June, United States. So we're really proud about that. So that was nice to get recognized for that. And I'm going to move on here. I also want to let people know that I know that Jean Perret is coming up next with a presentation. Jean's with Chemco. They represent us here in Canada. And we also work quite closely with Field Environmental Institutes of the United States, which have 13 or 14 locations. I'm saying that because I think they just opened a new one. I just had to verify that. COVID slowed things down. So just want to let you guys know about that. So I'm going to stop at that point. If there's one, maybe two questions, I think I can do that in the last minute and a half we have. Otherwise, thank you very much for your time.
Thank you, Bud. That was really, really informative. I don't see any questions on the questions bar. Anybody have anything? You can quickly type it in there. We've got a minute and a half left.
Can you hear me?
Yep.
Okay, any questions?
Oh, there's one. Oh my gosh, that's tiny.
Let's see.
Other than enhanced pump and treat system, what other remedies? How can I make this bigger?
Okay.
Here we go. What other remedies, surfactants, can be matched with? Other than enhanced pump and treat system, what other remedies, surfactants can match with?
Yeah, no, that's a great question. So that's a bit of physical, but I'll speak to three. But you can enhance pump and treatment, which is one of the things I originally wanted to improve. We also have people doing like multi-phase extraction, dual phase extraction, under different names, air sparging, even in situ, ex situ, biological, oxidative, aerobic, anaerobic, or facultative. We can actually improve those. We also have clients that are doing certain types of, like I know Jean's going to be talking about reduction of reductive chemical procedures. We can actually enhance those by desorbing and making it available. One thing I'm seeing on the pairing side quite a lot right now is where clients do have L-NAPL or D-NAPL contamination, and maybe they like using chemical oxidizing or reducing agent, but stoichiometric is too expensive to do that. So in those cases, we'll come in and we'll use our technology to basically reduce that free phase down to a sheen or less, stop, and then they'll proceed with maybe some continued physical, maybe a biological package or chemox, and or they may get themselves down to numerical or close and do a risk assessment for closure. So we're getting paired with all that.
Great, thank you. Okay, thank you very much, Bud. That was really great.
Thank you. Happy to be a part of this.
We'll turn it over to Jean Perret. He's going to talk to us today about in situ chemical reduction for remediation of soil containing chlorinated pesticides and herbicides.
Thank you, Holly.
We can see you. Your presentation's up.
Beautiful. So I'll just minimize the screen and then I'll be on with you. So Hello again. For those of you that had the chance to listen to Bonnie's presentation from Inotech a bit earlier, she was describing the Sterilant program that this organization is overseeing, trying to remediate the sites all across Alberta. The technology I'm presenting here has been discussed with the researcher, and we hope that in one of the stages of the program that we'll have to come and implement it on some of the sites. So with that said, just moving on about the outline of the presentation. I'm not going to go, I'll go quickly about who's Chemco, what we do, who we are for those who don't know me. I will obviously focus on in situ chemical reduction, so ISCAR, what it means on the chemistry and the biochemistry side. Then we'll talk about some specific applications that are targeting the deramin technology, talking about completed project and how we qualify and design these sites and evaluate them from here. What is chemical reduction? So, people are quite accustomed with oxidation. We see it every day. If you're leaving a piece of metal outside, it rusts. Well, that's typically adding, oxygen to the mix. The reductive is the exact opposite. So we're trying to remove these electrons, from the contaminant of concern. So one of the reductant that we're using to induce these reducing processes in the subsurface is ZVI, so zero valent iron. It's the mostly used material out there, and you can enhance or also do reductive condition just by adding fermentable carbon substrate. So I'll come back to this very often. So in the end, we're talking about either using biotic, so meaning processes that are using bacteria to conduct the chemical reduction, or abiotic process, which are strictly chemical reactions that are occurring on the reductive side. One of the I'd say parameters we're looking at is ORP, and I'll come into my presentation in discussing how important the ORP is when you're trying to conduct these chemical reduction processes on your chemical of concern. So on the terminology, so we got the electron donor, we got the electron acceptor, which is typically our contaminant of concern, and then as I said, the reducing species can either be an inorganic material like a zero valent iron, or it could be also fermentable carbon. So what are the advantages of doing ISCAR out there? First, it's a very low cost. It's not as hazardous as doing chemical oxidation, because most of the time we're working with stuff that is either food grade or agricultural grade. So it's nothing like tough to handle in sites. We're usually normally groundwater flow, the natural flow of groundwater to treat up, or we just have to essentially amend the soil to obtain a certain level of humidity to create the proper reducing condition. The ISCAR, in situ chemical reduction, can be used as itself. It also can be combined with other technology, as Bud just explained. If you have something that's tightly sorbed to the soil, you want to make it available. Guess what? You can just, get it to become available to the water phase by adding a surfactant and then complement or start your reducing condition afterward. So normally it's not applicable when you have very high loading of contamination. So if we're talking percentage-wise, like above 10,000 milligram per kilogram of contaminant, might not be your best bet on the economical side. And then, there's a few products out there that are available that are going to be using straight ZVI or a combination of ZVI with other type of fermentable material. So the range of contaminant we can target through reductive condition is quite extended. Usually you've seen it talked a lot on chlorinated ethylenes like PC, TC. So these type of compounds are quite often targeted through reductive condition. Pesticide, herbicide, guess what? That's the focus of our presentation. I do have a slide that is specific to that right after this one. You can target some energetic compound, so that's interesting. And then the metals. Metal stabilization is quite possibly, there was an Emera talk, if you've taken it this morning, that was exactly doing that, through the use of ferrous sulfate to stabilize copper, into an aquifer. So, and then you could do hydrocarbons on the reductive. It's not as efficient as going on the oxidative side, but guess what? It could happen. Same thing with pHs. Now, if we're focusing on the pesticide and the herbicide, the two compounds that are mostly of concern in Alberta are the bromacil and the turbofuran. So these two are really what has been hitting your site. Now, you could see here why they're so kind of persistent is mostly look at the half-life. It's usually very long before you're starting to see degradation, and it does make sense. These are sterilant pesticides, herbicides. They prevent bacterial activity or plant growth. So guess what? They are there for a very long time once they've been applied. Now, when we talk about chemical reduction, I did mention before that we can either do with biotic or abiotic compound. So these two, would combine into these four types of mechanisms. First, you got what we call direct chemical reduction, when your contaminant of concern would come in direct contact with the species of reduction. So then you got indirect chemical reduction, so where your iron would essentially dissolve in the water phase as ferrous iron, Fe2+, and then it would go and contact your contaminant of concern in that matter. Now you got the stimulated bacterial reduction, which is done through obviously the biotic pathways, as you're producing or adding up some bacteria that can possibly go at your contaminant of concern. We see that quite often with chlorinated ethyns, where we're using the allocococcidase to do enhanced bio reduction of the compound. And in all of these, you got the enhanced thermodynamics. So in order to illustrate these, I've prepared that little showcase here when you could see what is direct dechlorination. So you could start here with ZVI, which is the zero valent iron. And it would be a direct contact between the contaminant and the iron, so that electron transfer would essentially bring up dechlorination in that case. And so what we're trying to break here, in the same way matter in chemical oxidation, we're trying to break these carbon-carbon, carbon chloride, carbon bromide bond, or carbon hydrogen bond, so that at the end, what's left of our compound is really just carbon dioxide, water, and obviously if you have chloride or bromide, they would be there. Now, the big thing about doing pesticide and herbicide is we're combining all of these processes together by mixing the iron. So you can see here the iron matrix, the zero valent iron, and the organic carbon. And what that does is you would have obviously effect 1 and 2, as I've explained, through the indirect contaminant reduction. You got biostimulation, but mostly you got enhanced thermodynamic. And that's really key in what we're trying to achieve here, because there's a synergistic effect when you're combining both a fermentable carbon substrate and a ZVI compound. And it's explained within that slide here, where we can see typically when you're just using an organic amendment, you might fall off to -200, -300 millivolts on the ORP range. But when you're combining both, guess what? You're kind of doubling up. Like it goes down -500, -600. And in these very specific ORP level, there's kind of the energy that's required to decontaminate or break down your component is much lesser. It's much quicker. So you're getting a kind of a kick, an extra kick or a fuel boost to get at the contamination. So the product that was tested here in these research is typically composed of 40% ZVI and 50% organic carbon. And so there's in the organic carbon, there's some quick release and slow release, so we can get an extended effect from the mix. The emplacement technology now, and I'll revert back to the sterilant site field as I've discussed about, which usually contamination is found very close to the surface. So in these type of circumstances, what can be done is we can mix above ground, and some of the case study I'll be presenting will be exactly related to that, where we would mix in the organic substrate, the ZVI, above ground with the soil, and then we would essentially put water to obtain the necessary level of humidity to make the proper contact between the contaminant of concern and our amendment, and obtain the reducing condition given. And then after that, we would just let it be. So that would be kind of a on-site, but on-surface type intervention. This slide here describes what would be done in situ. So if you have, let's say, contamination that is much further down in the subsurface, so you could do obviously a hotspot treatment by injecting or placing your amendment down in the aquifer. You could do also plume control. So if you do have contaminated groundwater that's migrating off-site or that's coming into a site that you're trying to protect, you could apply these type of technologies on the reductive side as PRB, so a permeable reactive barrier setting. Emplacement, as I've explained, you could do direct trenching, excavation, or soil mixing, which it could be done above ground or deep soil. But also you could do direct injection or injection well or fracturing or jetting, of these amendments as slurry when you're doing into the deeper aquifers. About the synergistic effect and let's say the radius of influence that we can obtain around the area. So again, once you've in place your amendment, if you're trying to conduct straight chemical reduction processes, you could see here as a water flow from left to right, what kind of radius of contact you have. So, well, guess what? If it's direct, it has to be in direct contact. Then if you're using ZVI, it doesn't spread very far. Same thing with solid state fermentable carbon substrate. So it's minimal. When you got indirect, then your material typically ferments or get reduced and releases some of the ferrous iron in the aquifer, and then you're extending it out. But when you're combining both, okay, you're creating that vast plume, which is showcased in the lower right hand of the slide here, where you're extending the radius of influence of your treatment zone. So that means that you can distance your injection point or your amendment application. And you could see that here through that study that was released by URS in the US, where we've extended up to 3 meter down gradient from the PRB location, the effect on the very low RP zone that we were trying to conduct here versus the up gradient, which is again on the left-hand side. So when we're working on top of the soil, so it's obviously not in situ, it's still in situ, but as I said, with very shallow contaminated soil, then what we can do is do cycles. So each of these cycles, and you would see it here, so it starts starting up when you're putting your amendment, you decrease up to maybe 400 minus 500 ORP level, and then you would then move up slowly back towards aerobic oxic condition because you're obviously above surface and it's aerated. So if you don't reach contamination degradation fully at that time, what you could do is re-amend and then restart your cycle, and then you would cycle it back. So every of these kind of cycle would last anywhere between, I'd say, 10 to 20 days or 30 days, depending on temperature and soil type and water content. And then you would repeat that. So let's say that you need to achieve a 90% removal rate, but after one event, you only are getting about 50 or 60%. Well, guess what? You would just do another cycle and then move on until you reach up to the desired level of contaminant removal. All of these technology, and when we're talking about in situ, whether it's surfactant, oxidant, reductant, biological agent, bench scale is the key. You don't do it in the lab. If it doesn't work in the lab under idealized condition, your chances of success out there in the field are minimal. So please, please, please consult with your specialist. At Chemco, I think we've conducted about 50 or 60 bench scales so far this year. It's been a bit crazy despite of COVID, but there's a lot of labs out there that can help you out in achieving optimization of the chemistry. Just again, remember, if it doesn't work in the lab, it's not going to work in the field. And then, people that come to us and that ask, if we're interested, what kind of measurement we need to establish dosage rate, to establish, what kind of amendments should be required, and what the cost is associated with the project. Sorry, it's typically the data set that's required here. I'm going to move on to some case studies here. Just want to see how I'm doing on time. Not so bad. So the first case study is targeting DDT, DDE, and dieldrin. So it's a home builder site. So it's a brownfield that was in the Ontario area. And the soil impact, as you've seen here, they're very shallow, about 60 centimeters below ground surface. So we're talking very shallow contamination, and the remedial goal for both. So again, material is non-hazardous. So we're using agricultural equipment to have the tilling done with the soil. It's only 60 centimeters, so just these type of equipment can do it. Then and you'll see that process repeated. We make sure that we irrigate or water enough, put enough humidity in that soil to start our reaction. So the data here is presented on the upper table for one cycle. So you could see here the DDT and the DDE going out by about 50%, sorry, within one cycle. And then, as we didn't reach out our criteria for both, what we did is we repeated for a second cycle where amendments was added up. And we ended up with the necessary removal rate. So that was typically what happened there for that particular case. Now, just to showcase again, that's typically all the lots that were amended. And after one cycle, the green one were already at criteria, so we just finalized. And after 2 cycles, 100% of all the soil were treated. The good thing about this, and that's how we got approached and discussing with Inotech about the stirlant, is that this technology again can be brought to sites without a lot of risk. They can be applied easily, and the only thing you need to do is really water them up. And then once you've watered them, you just let them be, and you can return, after a few weeks and see if you've done to your criteria. Now, about the fate, what's happening really with dechlorination when you're dechlorinating DDT and DDE? So you can see here it's a very complex pathway. But kind of remember what I said early on. In the end, you're getting to that carbon dioxide and water, which is what you want. Now we've done C14 DDT fate studies, so just trying to make sure that it was not dilution and it was really mineralization that was happening there. And typically, we've seen that happening through the research. 2 other type of compound, dieldrin and chloridane. Again, here we're moving to Florida. The one thing good about Florida, if you're trying to conduct reductive condition using biotic remediation, guess what? It's very warm, so it goes very quick. So you'll see on this one that the standard again were achieved. So same thing, amendments, watering first, and in that particular one, I'll showcase the loading rate. We're talking about integrating in the soil matrix anywhere between usually 0.1 up to maybe 1% weight on weight of amendments, and that would be overall. So in this case, we've incorporated 0.5% of the weight of soil. We went and irrigated to about 90% of the soil water holding capacity, and left it undisturbed for 6 days. And then, we went back. So the cycle there that usually takes here about 20 to 30 days, over there took 6 days. And then we apply on the 8th day. So that you've seen before, tillage equipment. So typically the redox potential after 24 hours went from plus 126 minus 458, which is exactly what we want to see. And then you can see here the pH in the soil. About the reduction level, you could see up here that we had about 50 or 70% removal for both contaminant of concern, within 1 or 2 cycles. So successful remediation again, very short time frame because of the weather, and good cost because of the low level of amendment that was given in there. So just to say that these technology have been, and people are talking that it's not something that's coming out of the box this year. You know, they've been out there for the last 20 years. So we've done hundreds of sites applying Deraman on different type of contaminant. The real challenge for Alberta is the weather. You know, and it's true for Canada, but as I said, it's been achieved in Ontario. What we've shown, and that's coming from experience, you know, through all the sites we've worked over the years, for these type of chemical compounds and these type of reaction we're trying to occur, low temperature, what it would mean for us and for you is that it's slowing down the kinetics. So we're just looking at a longer timeline rather than it's not going to work. So if you're patient enough, you'll get there. And I've seen it through oxidative or reductive reaction on site. The other one's Elmira, Ontario. That's an old site, but it was 2,4-D and then DDT. The 2,4-D is something that's also used to make up the turbiturone. So it's chemically close to the molecule. So, and again, you could see here, you know, we're talking about 100 milligram per kilogram, so much higher loading of contamination here than in the other ones. And it took up to 9 cycles to get it down, but eventually got there. And same thing here for the 2,4,5-T and then the DDX. So it is something that is applicable to a lot of sites. That's another one that's done in Cambridge, where again, you know, it was reduced to 99% from the initial, you know, from 67 milligrams per kilogram down to 0.5. So testing, again, bench scale is really important to make sure that we can get to the level of remedial that we want. And then finally, the last case study is taxophene and DDT from 2009. Again, you could look here at, we started very, very, very high, you know, some example here. And you could see all the reductive, like, you know, and these are log scale. So we were able to achieve residential treatment centers. So we can get to very low level using these type of technologies. That kind of concludes the explanation I wanted to give you on chemical reduction processes to deal with sterilants, pesticides, and herbicides. For those who don't know us, you know, we have warehouses all across Canada, but really what we do is we specialize in assessing and supplying in situ technologies for treatment that goes from chemical oxidant, reductant, soil washing technology, you've heard BUD before, and then bio, and obviously permeable reactive barrier amendments. So with that said, I'd like to thank our partners, and especially Peroxium and RemTech that were part of putting that presentation together, and hopefully we'll have some time for questions. Thanks again.
Thank you very much. We do have a couple of minutes for questions. I don't see anything in the question box. So we'll just give it a second here. See if anything pops up. Okay.
That's good. Well, thanks, Holly.
Thank you so much. Thank you to all the attendees and to S2 Environmental again for hosting this session. And we'll have a good rest of the afternoon, everyone. I think there's a 10-minute break now, actually.
Correct.
Yeah.
Thank you.
So we start back up at 1:50. Thanks. Bye-bye.